Hi there, mathematicians. Let's get started with 4.4, Congruence and Transformations lesson. If you're looking at the textbook pages, the first page is your two explorations with the essential question at the top of the page. So let's take a look at the essential question here. What conjectures can you make about a figure reflected in two lines? And the two explorations are designed to explore that question. So if you have your calculators, definitely start practicing using your dynamic geometry software to draw any scalene triangle and label it triangle ABC, and then just follow each step instructions to kind of explore the ideas about reflecting across two parallel lines and see what you get. And you can see the sample picture here for exploration 1. And then the second exploration, reflections in intersecting lines. Exploring this idea with your geometry software, which is your calculators. You can create images similar to this. And your graphing calculators have the transformations within the geometry feature of your calculator. And counterclockwise rotations, practicing those skills. So let's move on to the next page is where we see the concepts explained. And our objectives are to identify congruent figures, describe congruence transformations, and use the theorems about congruence transformations. So we have here identifying congruent figures. Two geometric figures are congruent figures if and only if there is a rigid motion or a composition of rigid motions that maps one of the figures onto the other. This phrasing, if and only if, represents a biconditional statement, meaning if the hypothesis is true, then the conclusion is also true. And then we're seeing this rigid motion again in 4.4. We saw it earlier in 4.1 through 4.3. Here's the definition of rigid motion one more time. Rigid motion is a transformation that maintains length and angle measure. And here we see some examples of figures that are congruent because they maintain length and angle measures. They're same size, same shape. And here are some examples where we have shapes that look similar, but they are different sizes and different shapes. So keep reading and then looking at example 1, identify any congruent figures in the coordinate plane and explain. And really learn what it looks like to explain. And here's a great explanation model for you to start with knowing what kind of details we're looking for when we ask for you to explain. And we can see that quadrilateral ABCD is congruent to quadrilateral NPQR. The order of the letters matters, so you want corresponding vertices matching up with corresponding vertices. So A matches up with N and corresponds. B matches with P and corresponds. C corresponds to Q, and D corresponds to R. So when you name the shapes that are congruent, the order of the letters must correspond. So as you can see, square A corresponds to square N, and then B corresponds to P, C corresponds to Q, and D corresponds to R. Again, when you're naming congruent figures, the order of the letters matters. So we see that again with triangle KLM. So K, L, M is a reflection of E, F, G. So E corresponds to K, as it is in the statement. So K corresponds to E, and they're the first letters when you name it. L corresponds to F. So you see that L and F are the next letters in the lineup. And then G and M, and you can see that in the last letters of the stating that they're congruent. So triangle STU is a 180-degree rotation of triangle HIJ. So triangle HIJ and triangle STU are congruent. Again, order of your letters matters. I also want you to note that you can write your congruent statements similar to what we see here. Parallelogram ABCD is congruent to parallelogram in PQR, and we explained that it was a translation, and we defined the number of units and directions that the translation moved to map parallelogram ABCD onto parallelogram in PQR. We can also see that by reflection, triangle KLM is congruent to triangle EFG across the x-axis. So a reflection in the x-axis is an accurate statement to make. Then the final transformation is triangle STU congruent to triangle HIJ, and the transformation was a 180-degree rotation, and this is in relationship to the origin. For rotations, your origin is your center of rotation that we learned about in 4.3. Okay, so let's move on to the... Okay, on this next page we have congruence transformation. And we can see here that for congruence transformation, it's highlighted, so make sure you understand that vocabulary. And we can see our example, parallelogram ABCD maps to parallelogram EFGH, and making sure you can describe the transformations. We, in the previous sections, would name parallelogram ABCD mapping onto A prime, B prime, C prime, D prime, which is still okay, but you may also just rename, just have a completely new name for the image of a pre-image. And we can see the explanation completely here in this section where we see solution. So we can see that parallelogram ABCD reflected in the y-axis to get us A prime, B prime, C prime, D prime, which then translated to parallelogram EFGH. And make sure you read this completely to understand a full explanation. And then you can try one on your own as well. Okay, and on the next page with example 3, we see theorem 4.2, which has to do with reflections and parallel lines theorem. So make sure you read through this theorem to understand how parallel lines, when we reflect a segment or any figure for that matter, across two parallel lines, it's the same as a translation of the pre-image to the A double prime, B double prime in this case. And you can see example 3 explaining across lines K and M. And here's the solution. Make sure you know how to write your congruence statements, because all of these transformations are a rigid transformation. In other words, a rigid motion where length and angle measures are preserved. And then we have our example 4, which has to do with the second theorem in this section. The second theorem in this section has to do with reflections in intersecting lines theorem. And what this says is if I reflect across two lines that intersect, it's the same as a rotation about point P, which is the point of intersection where the two lines intersect. And there is a special relationship of the angles. So reading through this theorem to understand how a reflection across two intersecting lines is the same as a rotation. And then you see an example, example 4 with the solution, and then you can definitely practice one on your own, as you can see down here for monitoring progress, numbers 7 and 8. And this concludes our notes for section 4.4. So be ready to practice all of these problems in class. And if you turn the page, the next page, exercises 15 and 16 go with example 4. And then anything beyond 16 is just going to be a mix of different types of questions that you could be asked. And then as you progress through the exercises, the style and level of the questions do get more challenging. And so these are the type of questions where we definitely want to make sure we can start to really critically think and explain and reason about the concepts, and always do error analysis type questions as well. So come prepared to practice the skills, maybe struggle a little bit, and ask questions. So bring in questions that you already think you might have. And that's it for 4.4. Now please stop the video. If you need to rewatch it, please rewatch it to see if you missed anything that you need to capture in your notes, and then move on to 4.5.